Approximating areas under curves and displacement. And indeed, these two concepts are related. So, what is displacement? It's the change of position of an object. Basically, the final position minus the initial position. Displacement is not the same as distance traveled. Okay? So we could consider an example here. If you start in your home and get in your car and drive around, then come back home, well, your initial position was your home, your final position was your home, and so the displacement is going to be zero. There is no change in position when you consider that entire interval of leaving the home and coming back. What about the distance traveled? Well, as your odometer will attest, you've definitely traveled some distance by seeing that the number of miles has increased on your odometer. Okay? So that's the difference between these two concepts. Displacement is final minus initial position, and distance traveled is what you would see on your odometer. Okay? The actual length that you traveled. So if the velocity is constant, and velocity, not speed, velocity has a direction, speed does not. So if the velocity is constant, the displacement, which also has a direction, right? It could be positive or negative depending on where you are on the x-axis if you're moving in along the x-axis. So displacement also has a direction, is given by the velocity times the change in time. Okay, so displacement is equal to velocity times change in time. I didn't write that here, but because we won't consider it. But the distance is equal to the speed times the time. Okay, but again, we're dealing with displacement and velocity, and displacement and velocity are what's called, and what will become clear if you continue your studies, vector quantities. Okay, so they have a magnitude and a direction. Those are called vectors, and hopefully you will be lucky enough to learn more about those in the future. So let's take a look at an example. Find the displacement of a car that is traveling at a constant velocity of 60 miles per hour in the positive direction. So it's never going in reverse. Well, we have that the displacement is equal to the velocity times the change in time. This car has been traveling for 2 hours, and so the change in position will be 60 times 2, 120 miles. Okay? So the change in position of this car will be 120 miles. And what did we actually do here? Okay? Well, we have a velocity function, and it's constant. This constant function in blue that you see there, equal to 60 miles per hour. And we multiplied it by 2, the change in time. And here we're starting our clock at 0 so that the change in time is actually equal to the time. But at least in this graph. But the area under the curve, in fact, gave us the displacement. Okay? And this makes sense because we have units of length over time. Okay, that's the velocity. This is represented by that blue curve there. And we're multiplying, to get the area, we multiply by the length along the t-axis. Okay, that has units of time. So we're taking a height that's in miles per hour, and we're taking a time that's in hours. So we're multiplying the length times the height to get the area. And so you are getting miles per hour times hour in units. And you see that the hours cancel, and you end up with the miles that you see there. So we have the correct units, and the concept makes sense that, we're looking for areas with the t-axis and the velocity axis there. Now, how would the position look? How would the position look? If, and this is a big if right there, if we start at 0 miles, so wherever we decided for our origin, you could say that I'm going to set my origin at my garage, okay? So if you know, that's going to be the 0 position. So if you start at the 0 position, then the graph of displacement will look like this, okay? So it increases linearly with time, all right? And notice something here, that the derivative of this position function is equal to 60, which is the velocity function, okay? And what if we didn't start at the origin? What if we didn't start on x at t equals 0 miles? Well, then this curve would be shifted up or down, depending on where we began, but it would still have the same slope, okay? That same slope of 60 miles per hour, no matter where you begin, okay? And that's what's important here. We're finding the displacement, the change in position. So no matter where you start, your change in position will always be 120 miles. Okay? If, in addition, we make an assumption of where we start, then we could plot out the position function in a unique way. But no matter where we begin, the beginning and end points will always have a height of 60, even if we started over here or over here. So over 2 hours, it will always be a change in height of 120 miles. Well, that's all nice and well when you have a constant velocity. Okay, here we had a constant velocity of 60 miles per hour. Well, what if your velocity looks more like this? It's not constant and it's changing. What do we do in that case? Well, it's still true that the area under the velocity curve will give you the displacement. Okay, but we're going to need some sort of trick. And here's how to do it. Okay, here's one possible way to sort out this problem. You'll say, okay, over the interval a to b, the velocity is indeed not constant. Okay, so I can't just take the velocity and multiply it by some time. But what if I consider very small time intervals? Now, unless someone's accelerating at an extremely fast rate, we could choose a moderately small time interval, and within that small time interval, the velocity will be constant. I mean, consider, say, let's label this point here. Let's call this C and D, okay? So from C to D, is the velocity changing? Yes. But it's barely changing. So why don't I just choose a representative velocity there, okay, for that whole interval? I'll just pick one out, say the midpoint between C and D, and I'll let that be the velocity that I'll choose to be representative over that subinterval. And so if I wanted the change in position from C to D, the displacement from C to D, I'll just take the velocity at time t2 right there, okay, t2, and multiply it by the change in time from time equals C to time equals D. So that's how much time goes on from in that small time interval, okay? And this will give me my change in position over that small time interval. And you might say, well, you know, you picked out a special velocity. That's just at t2. It's not all throughout the interval. The velocity is actually changing. Of course it is. But if we keep choosing smaller and smaller time intervals, subintervals, if we break up the interval a to b into very small pieces, then any velocity that we choose for this continuous motion will be a pretty accurate approximation for the rest. As you could see here, it's barely changing. So it's accurate. It's not perfect, but it's also not bad if we break up the interval into sufficiently small pieces. And so here we have that the displacement, the total displacement, so what's the change in position from time equals a to time equals b, that total displacement is going to be the small displacements, okay, over each of these intervals. All right, so we broke this up into 6 different intervals. That way the velocity is approximately constant within each of these. And this is an equal sign, okay? The approximation hasn't happened yet. This is still an equal sign. And you could see that it's equal, say, for example, by considering, say, delta x1. Delta x1 will be equal to the final position after the first small interval. So that's going to be x at t equals c minus x at t equals a. And take a look also at delta x2. Well, that's going to be x at t equals d minus x at t equals c. Okay? Well, we've seen that x at t equals c before, right here. So when we actually add delta x1 to delta x2, this will end up canceling. Okay? And in fact, all of these middle, the middle intervals, the intervals of our the endpoints of our subintervals, will end up getting canceled, and you will in fact get just x at time equals b minus x at time equals a. So the point there is that this is indeed an equal sign. We still didn't make an approximation. Where does the approximation slip in? It slips in here. It's by saying that this displacement from time equals a to time equals c there is approximately equal to the velocity at this special time. Okay, we just decided to take the midpoint between a and c, but we could have chosen any velocity within that subinterval. Okay, and we're going to multiply by delta t. And what is delta t? Delta t is the length of each of these subintervals. Okay, so delta t is the length of these small subintervals, that small time duration. And so this is an equality, and then each of these is approximated by these. Okay, and it's an approximation because we're picking out a specific velocity. And indeed, this will give us an approximation for the total displacement at the end. I just want to make a remark here that we partitioned the interval a, b into equal length. We didn't have to do that. Okay. One may argue, well, the velocity is approximately constant throughout this whole thing, so just use one, an interval that long for that one. That's perfectly valid. Okay, but we're choosing to partition into equal lengths. And we also chose special times to evaluate the velocity in the midpoints. But we didn't really have to do that. We could have also chosen say instead of T2, I could have chosen C or D or anywhere in between. Okay? But just for this example, we chose the midpoints, and we chose to partition our time intervals into equal length time intervals. So let's take a concrete example. Okay, we're going to approximate the displacement for an object that's moving along the line, okay, just in one dimension, with the velocity of that object given as a function t squared, okay, given in meters per second there, and so this is also in seconds. And we're interested in the time interval from t equals 0 to t equals 8, okay? And clearly the velocity is not constant, it's increasing. So it starts out at 0, and then by the time you get to t equals 4, it's the object is moving at 16 meters per second, and on and on. So it's getting faster, and it's getting faster at a rate of t squared. So how can we do this? Let's partition our interval 0 to 8. We're going to partition it into two, okay? Two different sub-intervals. And so if we partition 0, 8 into two equal sub-intervals, then each one of these will be have a duration of 4 seconds. And so the first sub-interval is 0 to 4 seconds, and then the second sub-interval is 4 to 8 seconds. And let's also choose a representative velocity for an entire sub-interval. And here we're going to choose the midpoint. So similar to what we looked at above over here, okay? So what's the midpoint then of 0, 4? It's t equals 2, and the midpoint of 4 and 8 is t equals 6. So that's where we're going to evaluate the velocity. Okay, so we want the total displacement from t equals 0 to t equals 8, which looks like this. Well, that's equals to the displacement from 0 to 4 plus the displacement from 4 to 8, equal. And now the approximation occurs when we say, well, we're going to say that this car is going approximately equal to this v at t equals 2 throughout the duration 0, 4, and approximately equal to the velocity at t equals 6 throughout the interval of 4 to 8, okay? And our delta t here is the time of each of these, change in time in each of these subintervals. So it's going to be 4 seconds. 4 seconds goes by in each of these subintervals. So what's the velocity at time equals 2? Well, we have the function. It's t squared, so it's going to be t2 squared meters per second, so 4 meters per second. And the change in time is 4 minus 0, so 4 seconds. And what about the velocity at t equals 6? Well, 6 squared is 36. So it's going, so that's what we chose to be the representative velocity in the second subinterval, 4 to 8. And what's the change in time? 8 minus 4, 4 seconds, okay? And we get that the displacement is approximately equal to 160 meters. So here you could see how the velocity curve would look like with v equals t squared. You see that black curve there is the velocity curve, okay, as a function of time, the t-axis. And we chose two subintervals. We approximated with two subintervals. But what if you just decided to use just one interval? Okay, so you just consider the whole 0 to 8 seconds, and you only pick out one velocity throughout there. Which velocity should you pick? Well, you could maybe choose that middle one. That's what's going on here. So we could evaluate the velocity at t equals 4 and multiply it by the entire change in time, so 8 seconds. 8 seconds times the velocity at t equals 4, which is 16. 8 times 16. What is that? That's going to be the area of the pinkish rectangle that you see there, okay? But that's not a good approximation for the area under that curve. So let's break it up into two. This is what we did, okay? And we chose the representative velocity to be the one at t equals 2 for the first subinterval from 0 to 4. And then we chose the representative velocity at t equals 6 for the interval from 4 to 8. Okay? And we got 160 for the total displacement. But as you could see, still not very accurate. So what would happen if we continued to break up this interval 0, 8 into smaller and smaller pieces? So here we have 4 subintervals, 8 subintervals, 16 subintervals, and notice here that at 8 the displacement is 170 meters. 16 it's 170.5. So then we're approaching a pretty accurate displacement at this point, breaking it up into 32 pieces and breaking it up into 64. And now, of course, you're probably thinking, well, when does this stop? Okay. Well, we can continue breaking up this interval 0 to 8 into smaller and smaller pieces so that n goes to infinity. And at the limit that n goes to infinity, you're getting exactly the area under the curve. We'll talk more about that when we discuss the definite integral.